Okay, so let's just get on with the session. The first speaker is Condie from New Mexico, and it's perfect for him to start this off because he's one of the grand synthesizers of the secular evolution of continents, formation processes.
Well, I'd like to thank Cinti for inviting me to be part of this. It sounds like it's going to be a really exciting discussion group with so many disciplines represented here. And I hope to learn as much from it as anybody else, actually. And as he mentioned, I'd like to keep it rather informal. It's kind of hard to see in the dark out there, but if you have questions as I go along, feel free to bring them up. Because sometimes I assume things that probably I shouldn't assume. I'm not going to try to cover everything here today. A lot of what I'm going to talk about, in fact, will be introduction to what we're going to get more specific talks on and a little later, as I see from other people's talks. But I decided to focus on three main aspects of continental evolution, and three that are really hot topics today, and in some cases relatively controversial. Episodic ages and their meaning, how and where we produce new continental crust, and then finally the whole question of recycling continental crust back into the mantle. When I was a grad student at La Jolla back in 1960, I remember Golden Gastel presented a paper in one of our seminars, and this is his slide from that paper. And based on potassium-argon ages, he suggested that there were groupings of ages with a function of time. This was in 1960. We had some evidence before then that there were populations of ages, and he went on to propose that, in fact, this was a global event. It wasn't very well accepted at that time. A few years later, I compiled data for an earlier edition of my plate tectonics book, and I've got it here grouped in three geographic areas. As you can see, the important thing is here, these are, again, mainly potassium-argon and rubidium-strontium ages from those days, but we can still see, especially here in North America, in the Baltic Shield, evidence of groupings of ages, episodicity. And this was in 1976.
Kent,
Sorry.
may I start off by asking what is meant by an age?
Can I ask that question, ask you to say who they are?
Bill McDonough.
Yeah, we're talking about isotopic ages here, and there are many different methods we use in geology, of course, to acquire these ages. And to attach significance to an age, that is, how many billions or millions of years ago we're talking about, we have to have geological information. So an age is a more difficult, it's a concept I can see, because the mere presence of an isotopic age doesn't necessarily date any given geologic event. That comes from tying the isotopic age to the field relationships in geology. You've got to have both to understand what an age might mean. And you can still be wrong because in geology we have superimposition of various processes. We can have an age of an igneous rock that's then later hit by metamorphism, and then it's had deformed sometime later in that. And what we're trying to do today is pick out isotopic systems that can see these various events that have affected the original formation age of the rock. We're not there yet, but we're getting there. 1987, I updated this again. I said, well, maybe if this is a bias in sampling, since 1960, that these minima in here are going to fill in. But as you can see, they haven't filled in. And now this is based on zircon chronology, which we think is much more robust in identifying the ages of the igneous rock protoliths anyway. And we see these spikes are still in here, and especially one at 2.7, which I'm actually going to say something about later when we talk about this event. Zircons enter the picture. Now, zircons entered the picture many years ago. In fact, in 1960, George Rutherford, who was at UCLA at that time, was doing developmental stages on zircon chronology. I remember him giving a talk at La Jolla on his method that he was proposing then, the isochron method. Anyway, today we have many approaches to zircon chronology, and with two new instruments that we use, the laser microprobe, ICP-MS, inductively coupled plasma mass spectrometer, and SHRIMP, which is an instrument where we can bombard zircons with high ion beams. We can look at very small areas in zircons and get isotopic ages from those areas. In the case of ICP-MS, we're talking about somewhere between 20 and 40 microns in diameter. In the case of SHRIMP, we're down to 1 or 2 microns in diameter. This has provided a means for us to look at zircons. Here's a complexly zoned zircon where we can actually, here's a pit, an ICP-MS laser pit. It's like a little crater. Here's the magnification of it here. You bombard this area and you burn your way into the mineral, and you knock out element ions here, which are activated, accelerated in the mass spectrometer to look at their mass distribution. And for instance, in this very complex mineral, there are 2 areas that have been dated separately. Well, we can look at different areas in here. And what we're seeing is that zircons very often don't give a homogeneous age. A single zircon can give more than one age. And in fact, in some cases, it can be very complicated. It can give several ages. And then it becomes more difficult to assign or to interpret what those ages mean and how that zircon actually grew. This requires a lot of work of separating these zircons out and mounting them and analyzing them. Once the analyses begin, when I started on this at Macquarie University in 2002, I could do about 30 analyses in about 6 hours. That's all the patience I had to sit in front of the computer screen and watch these things come out. Some of the students would sit there for 24 hours. I couldn't do that, but you can get a lot of data in a short period of time. The precision of this is less than our typical SIMS data, our regular mass spectrometry data, which involves solution of the samples. 2 standard deviations are usually in the range of 20 to 30 million years here. That would make a lot of difference in young samples, but in old samples that we're generally dealing with in the origin of continents, 20 to 30 million years is a fairly small error. Detrital zircons have become very important. So what are detrital zircons? These are zircons that are weathered from their source area. They're transported and deposited in sediments. And then we go and collect those sediments. They may be sedimentary rocks if they're old. And we separate the zircons out of them. Now, the zircon ages we get out of those are not the ages of deposition of the sediment, but they're ages that reflect the source material of those zircons, where they originally came from. There's been a lot of interest. Here's some detrital zircons. Notice they're rounded. And also, if you look at the structures inside of them, they're really complicated. Again, you can get more than one age out of these zircons. And the challenge is to decide what those ages mean. Now, detrital zircons have taken off in the last few years because one explanation of these peaks that I've talked about is that they're sampling biases by geologists. Geologists work in areas that are of interest to them or of interest to mining companies, or they're easily accessible. And that's where the work has gone on. And so perhaps the valleys between the peaks are areas that are not so desirable to work in on this planet. Well, many, many years have gone on, and we still haven't filled those in, even though a lot of work has now gone on in some of the undesirable areas in the jungles of Brazil or Africa. But the interest in detrital zircons, I'm sorry, yes, I see somebody with their hand up.
Yeah, I was just, I know that you were totally fair or accurate with regards to the precision for laser ablation. I mean, for Phanerozoic zircons, it's like a 2 to 3%.
Yes. Right. This is for Precambrian zircon.
Yeah, for Precambrian, if you're looking at the absolute term, it feels about 20, 30 millimeters.
Yes. Yeah. What was I saying? Oh, about sampling. So the idea is that rivers may not have a bias. They sample where their tributaries go. And so if we look at the distribution of ages that river systems have sampled, we might get a better sampling of the continents. And so it became very exciting to immediately start to sample detrital zircons. So people started running to the mouths of the major rivers on the planet, the Amazon, the Mississippi, and so on, and collecting samples of sand and taking the zircons out of them to get a better picture of what the continent looked like. Well, as we're seeing, there are problems there, and I'm going to mention some of those in a minute. Rivers aren't all that biased. They're biased perhaps in a different way than geologists are biased. There are 4 problems in particular that I point out here. There are others. Some river systems, especially if they're small river systems, may sample rocks of a given age, and they're biased towards where their particular tributary systems are. Sources may not be preserved due to erosion or supercontinent breakup. This is a major factor that has been overlooked, in my opinion, is when supercontinents break up, the source area of some detrital zircons may disappear as a fragment of that supercontinent moves someplace else. It may not even be on the same continent. Many investigators have taken the area of cratons of known ages. This is particularly true of North America, where we have a pretty good sampling, or pretty good information on the distribution of these. Look at the area and plot it as a function of the detrital zircon ages. Try to correlate the two. But it turns out that detrital zircons, as a number 4 down here, they come mostly from older sedimentary rocks, not primary sources. For instance, at the mouth of the Mississippi, we get virtually no ages that are 2.7 billion years in age, and yet all of eastern Canada is a province that has 2.7, very widespread. Why is that? Some of the tributaries of the Mississippi go up into that area. Probably the Mississippi zircons are not coming from the Archean cratons in Canada or even in areas in the U.S. They're coming from sedimentary rocks, such as the Permian section, which is very thick in southern New Mexico and in places in the southwest, which tributaries of the Mississippi are sampling. And so you're seeing resampling, if you want to think of it that way. And in the Permian, South America was backed right up in terms of where it was just before Pangaea began to break up. So we may have had sources from South America that are no longer with us. They're in South America someplace, if they're preserved at all.
Can I ask a question?
Sure.
Roberta Rudnick, I wanted to ask about your number 1 there. I don't think I fully understand it. You say river systems preferentially sample rocks of a given age. And do you mean that you might have a whole diversity of ages within the drainage basin of a particular river, but you would sample preferentially only one or several of them and not all of them? And if so, why is that?
Well, what I'm getting at here is the tributary systems. You may have a tributary system that samples only part of that. Yeah, you have a lot of diversity of age, but you're sampling that tributary system, okay?
You're just talking about sort of regional, small regional drainages,
right.
As opposed to large.
Yeah, the larger the drainage is, the more apt, of course, you are to sample a more representative sample of the area. Yeah.
Hi, Lou Derry. I'll try and show this if I remember on Friday, but even large river systems can be strongly biased in what they sample. And we know that the rivers draining the Himalayan front are essentially most of the tidal sediment is derived from a relatively narrow belt of rocks, despite the large drainage area of the basin. And there's a strong sampling bias in that system.
Mm-hmm.
And why?
We've got some sort of tectonic erosion feedback there, where we remove mass, we create topography. That topography is steep, it interacts with climate, we remove mass. And so for a very, very long time, relevant to any sort of isostatic adjustment or like that, we've had this one geologic unit that dominated the sediment flux out of the Himalaya for 20 million years or so.
It would also depend on It would depend on what rocks are exposed in the Himalayas, too. If you had some Archean slices up in there, or you didn't have those.
I'm not sure that, I think this is a functioning result of the tectonic picture, not so much of the age of the rocks per se,
Mm-hmm.
but because of the tectonic and has for quite some time on what essentially is the largest modern sedimentary deposit in the world. So the bias is very clear even on a large scale. In some cases, it might not be in the Orinoco or something. Well, even there, actually, the Andes long ago, or the Amazon was long ago shown to be dominated by Andean sediments, despite the large area of craton in the lowlands.
Well, clearly this is a problem that I think needs to be given more consideration. A lot of papers have been written, and they sort of ignore this problem.
Right, and just one more comment, I guess, about number 2, the idea of supercontinent breakup, and so the source is moved somewhere else that doesn't exist any longer, but in where the river's currently sampling. But whether that's a problem or not would sort of depend upon what questions you're asking.
Yes, it would. Yes, it would. I assume here you'd be looking for the source.
Comment to follow up on this first, Rebecca, just to make sure I understand what Lou's saying correctly. What I understand is that for a given origin, however the erosional system is set up, once it's locked in, then there might be feedback with eroding a particular rock. But we're not talking about differences in erodibility. So for a given origin, we might have a bias, but if you have a large enough sample, then overall it should be unbiased. You might be selectively picking different places of an origin, but it's not like there's an overall global bias in the age that we're talking about.
That may be. I think that's undemonstrated one way or the other, because I'm not sure that experiment's been done, or is even very doable. But presumably the large numbers should catch up with you eventually. But how large that number is not entirely clear. But right now we can say something like some 10 to 15% of the world's sediment is derived primarily from a particular lithologic unit. So at least in the short term, that's a pretty strong bias.
Okay, one final one here. Radiation damaged zircons, which tend to be the older zircons, may be undersampled because they don't survive the erosion cycle. Rick Astor and I got working on this. Rick's a seismologist. When I started having large databases, I needed somebody that was familiar with dealing with large numbers of data. And he's written a book on this, and he started to work with me. This is a diagram that he constructed when we only had 9,000 detrital zircons. Today we have about 40,000 in here, and the general picture is not changed from this. But here we see a plot he made of kernel bandwidth as a function of, over here, the intensity. It's just color-coded over here. And you can see the peaks are still showing up very beautifully here. This is 9,000, and those same peaks. This is the 2.7 peak. This is one at 1.9, 1.0, 600 million, and 300 million. Those 5 peaks were very robust when we did this, and they're still robust today. This is a global population now. In any given geographic area, they may not all show up. In fact, they don't. Down here is the peak confidence level. And again, those that are deeply red are most confident. And if you look down here, maybe you can't see that. They basically correspond to the same major peaks up there, the ones that we're most confident in.
Sorry, Meredith.
Sure.
What kind of a kernel are we talking about?
This is a moving window that we place the data in, okay? And he started out with a very small window, as you can see. I don't know what the smallest size he started out with. And he changed that window up to a very large window. And as you can see, I didn't mention that, but he felt that the best resolution actually came out with a kernel or a bandwidth between 10 and 30 million years between those two white lines where you had the peaks best defined. As you get down here and you widen the bandwidth, they're not near so well defined.
Is it a fancy kind of a histogram?
Sorry?
Is it like a...
It's like a histogram, yeah. Mm-hmm. Well, the problem that I've always thought about, and many others have thought about, if we have an Earth, this is Earth's temperature, say an average temperature, falling with time due to radioactive decay primarily and cooling of the core, why should you have spikes? Why should you have events on here? Why should not the age of the continental crust follow some sort of a curve that's parallel to that? Where do these guys come from? And there's been many models out there that have suggested where they come from. What do these peaks represent? Do they represent new crust or some sort of preservational bias, or perhaps a combination? How are the age peaks related to the supercontinent cycle? And in what tectonic settings and at what time did most continental crust form? These are three basic questions that a lot of people have addressed and are continuing to address and continue to be the subjects of a lot of discussion. This is a graph that Rick Astor and I put together from one of our papers a few years ago, showing the zircon age spectra. And here we've looked at it in terms of orogenic granitoids. These are granitoids from deformed areas, origins, bedrock. Okay, these have been sampled by geologists. Modern river sediments, ancient river sediments, and then this combines all data. Regardless of which of these you take, you can see an age spectra in here, and you can see peaks in here. And the peaks are these 5 peaks. They routinely come out regardless of whether you're dealing with a global spectra of orogenic granitoids. And incidentally, we've added to the database here, and the peaks basically remain where they are in all of these. This gives us some confidence that when you look at global databases, that the detrital spectra and the bedrock spectra are telling the same story in regards to where the big peaks are. Okay? Now, there are smaller peaks in here that indeed don't show up in all of these. Up at the top is the supercontinent cycle in purple, where these come together. The only supercontinent we really have a lot of data on, of course, is Pangaea, or perhaps Gondwana. But we have other supercontinents. 2 of them have actually been given names, but the configurations of these, I think I would confidently say now, are not very well known. We get various papers published every year of new configurations for these 2 supercontinents. And probably we had several super cratons, large cratons formed at the time of this 2700 event back here. Breakup times are in blue. Breakup times correspond, of course, mainly to the valleys in these.
So is it 1,000 different in that the orogenic granitoids are not showing it really? Or is that just the sample?
No, that's real. And it may be a sampling bias. Something I didn't emphasize enough here is in the bedrock samples down here, these peaks, some of these peaks here, depend on how many samples come from a given geographic area. For instance, this peak and this peak and this peak, if those 3 areas happen to be sampled more by geologists for some reason, those peaks could be very large peaks instead of very small peaks. And so down here in the orogenic granitoid sector, the height of these peaks you've got to be very suspicious of, I think. And I've got a slide here that shows this. We could actually bring that up. I don't have it in this group. The 2.7 peak over here is very big. If we take the Superior Province out in Canada, this is a global peak. We take it out, that peak breaks into 2 or 3 other peaks, and the 2.7 disappears. Yeah.
James Lee from New Mexico. Does your data including this sort of Central Asian orogenic belt? Because in that area we have a large event of 500 million years. And that one's doesn't really quite...
I don't remember in the young ages here our geographic distribution. When we put this slide together, there probably weren't not a lot of data from the Central Asian orogenic belt. Probably not a lot of data. No. Yeah. Yeah. No.
I'm just curious as to how you guys decide when you have a peak as opposed to noise.
Yeah. We've been working on that. Rick has some statistical tests that we've been applying. In this spectrum, we're just looking at the large peaks here, which are relatively obvious in most cases. The smaller peaks here, I wouldn't hang my hat on in any case. But we're working on a way to statistically define what a peak is and what it isn't. But as I say, I'm not so concerned about that because these peaks can come and go with geographic sample biases. you see. I mean, if I wanted to make that peak bigger, I'd say I'd hire 5 geologists and geochronologists to go into that area and sample it like the dickens and get hundreds and hundreds of samples. And then that peak, instead of being there, would be there. Okay.
The related question to that is how many geographic regions are sampled in these bigger peaks?
In the large peaks, hundreds, especially in this peak and that peak. Hundreds.
How come you can't, have you weighted it by area of bedrock?
Yes, we have.
Does
And
that look similar?
well, the only place we really have enough geographic information to weight it by bedrock area is probably North America and Baltica. And in terms of the 2.7 peak, no, it doesn't. And I think it's for the reason that I talked about, that you have recycling of zircons that have come from other source areas, not the Superior Province, for instance.
So another question, Richard Allen. So are there other people who've tried to do this and they have a competing plot, for example, or does everybody always see the same piece?
Yeah, one of the first papers that worked on this was a guy named Ayazuka. I don't know him, from China. And he correlated in North America the peak heights with geographic areas and felt he had a correlation there. The problem was that the zircons weren't coming from those areas, or most of them weren't. They were coming from recycled areas. Somebody else sampled the mouth of the Mississippi. In fact, we've had 3 independent groups sample the mouth of the Mississippi River. They all have different age spectra. The 2.7 peak is not even at all represented in one of them. And this is worrisome. What does that mean? I mean, what's going on with the Mississippi that you're sampling at the mouth of it, and the major peak there shows up in only 2 of the 3 samples? I think we have a lot more to learn about how rivers are sampling the continents. I think we have a lot more to learn in that area, and that's one of the questions that we can throw out here for more discussion.
Maybe the way to do it would be to create a composite sample that represents the entire delta region. Just take.
That's a good idea, yeah. Yeah. Sample many locations in the delta region and put it together as a composite, and then look at each individual sample separately to see what the variation is, if there is variation. Yeah.
Gee, Humphreys, I don't know my zircons that well, but I'm wondering how much, if you have a supercontinent assembly event, how much you might create some local granites in that collision and associated zircons, and then erode them in that event, and you're really seeing a relatively small scale process compared to continental creation per se. So what do these zircons actually represent in terms of what's going on in Europe?
That's the question.
Yeah, that's right. And that's the reason we've chosen to look at large populations rather than small initially. Because small populations certainly have biases like you're talking about, I think. And a peak can come and go, even in the detrital spectra. A peak can come and go, depending on how much is sampled in a given river system of that age. Somebody back there, yeah.
Yeah, that means, I was just comment that I think you're probably totally missing Antarctica and Greenland. I know they've been sampled because there are cons around the periphery, but you really don't have an idea even for the relative age of most of the bedrock.
That's true in terms of the detrital zircons. There's nothing from, I don't think, either one of those. But in the bedrock zircons, we have quite a bit from the perimeter areas in both of them. Well, certainly Antarctica. Sorry.
I just wonder if some of these events represent some major tectonic events, like you have the Pan-African events, and I mean that particular event about 500 million years ago, and you get lots of condie, and then those, you get both zircon and detrital zircon dating, and you get a lot of data, and that's going to basically tell you tectonic event.
Yeah, again, the question comes of associating the zircon age with the geologic event. Yeah, that's the real question that is.
There seems quite a bit of association of 1 billion years old. That's basically Greenville, right? I forgot what's 1.7, 2.7.
Well, Grenville actually has about 3 or 4 peaks in North America, but Grenville occurs on other continents too, Grenville age material. And there's a range of peaks within this window that I showed there, from about 1200 to 900. There's a range of peaks geographically in that time window for Grenville. Anyway, if we look at here, I put this cartoon-like cross-sections together to show where we form new crust. Here's a collisional boundary, a continental arc system here. We can form new crust. We can also bring terrains in and accrete them in here. And in a collisional origin, we think that this is where we actually preserve crust. It gets caught up in the collision, and because of the buoyancy of crust on both sides, it resists recycling into the mantle. Some of it, of course, is recycled, as we'll talk about. This is a recent configuration based on the work of Sergei Pisaresky, who is, I consider, one of the most precise and cautious paleomagnetic people in the field today. There are a lot of paleomagnetic reconstructions of supercontinents, but I thought I'd show one here. This is, he has some very robust and rigorous filters that the data must go through before he accepts it, including the magnetic data and the age data. And this is a construction which would be at about 1600 MA for the pieces at that time. And I have superimposed on his configuration the age of origins, which we're working on now, into 4 categories here, and they're color-coded. And you'll notice that the older ones here, the brown ones, which are 24 to, I can't see what, a 1900, and 1900, 1800, the blue ones, are very widespread in this group of continents. This is Kalahari up at the top and Laurentia down here. This is a time that these were colliding and making, if you want to call them, supercratons. The last 2 colors, which are down around 1700 to 1500, are all down here in Antarctica and Australia area. And this is the last collisions that formed this supercontinent. It's interesting how their geographic distribution is different there. Some of these smaller pieces, clearly we don't know the position of North China and South China. Every time I look at a map of somebody's configuration, they're in a different place. So you could almost say we really don't know where those 2 pieces are very confidently. I'm going to be talking about juvenile continental crust and reworked continental crust, and I'm just indicating what I mean by these. Juvenile continental crust is crust that comes from the Earth's mantle. As I'll talk about in a minute, this takes at least 2 stages to do that. But it carries a mantle signal with it, both in terms of trace elements and isotopes. Reworked continental crust is older crust that's been metamorphosed, deformed, partial melted. It's just been through the mill more than once, but it's not new material from the mantle. If we look at the sites of juvenile crust formation, I've divided them into 3 categories here. Of course, the ocean ridges, arc systems, we get here in the mantle wedge, and fluids coming in here and melting the mantle wedge. And then mantle plumes. Here we have a mantle plume. And mantle plumes can produce material which is extruded in our large igneous provinces. Some of it, in fact, some people think most of it, is not intruded, that it is underplated. And this is one of the real uncertainties we have at the question of continental growth at the present time. We think that most continental growth occurs here at convergent margins, and more precisely, Alfred Kroner and I have written a couple of papers on this, at continental margin convergent margins, which presents some interesting problems. But the question is how much material is brought up and underplated under the continents that we're not counting, okay? And we really don't have ready access to. This is one of the questions I wanted to bring up later. I think this is one of the major questions we need to address in terms of continental growth, is how much material is underplated under the continents. And that might be a question that can be addressed multidisciplinary with seismology and crustal xenolith studies and such.
I have a
Yes.
So you always talk about the crust, but shouldn't one really talk about the crust plus the lithosphere? In doing all of these.
Well, yes, in that they probably, at least in part, form together. The mantle lithosphere, of course, you may have added to later, too, also, and you may have added to the crust later. So I think it depends on the question you're addressing, whether you should call it the lithosphere or talk about the continental lithosphere or the continental crust. It depends on the question you're addressing, I really think.
But if you're talking about underplating, you're really underplating.
That's right. Some of that underplating would probably affect the lithosphere too, correct, yeah. This is a picture of some juvenile crust in the Pilbara in Western Australia. We have zircon ages from some of the associated felsic rocks in here, 3.46 Ga. Beautiful pillow basalts here. This is some juvenile and reworked continental crust from Zimbabwe. It's an area we studied many years ago. The numbers on here are units in here. We tried to come up with a geochemical story to see if these were all related by melting and crystallization, and they could not be related by melting and crystallization. There's clearly metasomatism and other processes. But this is a rock type we call TTG, which stands for tonalite, trondhjemite, and granodiorite, which are three compositional end members. And these are very common in Archean felsic crust. And we think they're the primary building block of Archean continents. And we find them today. We find them all through time. They're forming today in some arc systems. But as you can see, they're exceedingly complicated. There are these black units, which are amphibolites, which are mafic rocks, which are trapped in here and broken up. They may have been dikes, some of them. And then there's the felsic units, the cross-cutting ones, are clearly melts of material that have injected into this. So TTG complexes are very complex and they're very, very difficult to sample. Now, if we look at how we make continent, I just wanted to go through this briefly. We start out with the mantle, and I actually have a suite of rocks over here, which I'm going to put out here. This is my tutorial for this class. So everybody should come up and look at these rocks. I'm sure you're not going to be able to see them from where you're sitting, but I think there's nothing more humbling than to look at an actual rock, you know, especially for people that don't look at rocks very often. But if we start with this rock, this is a garnet laterite, which we're going to say is a piece of the upper mantle. Okay, and you can see the garnets in here, and you can see many of the other minerals. You need to come up and have a look at that. We're going to melt that, and when we melt that, we get a mafic rock, a basaltic magma. And that basaltic magma can crystallize, and if it crystallizes in a hydrous environment, it can crystallize to an amphibolite, or it can crystallize to a gabbro and then be metamorphosed. And I have two pieces of gabbro up here. One is a garnet gabbro, or garnet amphibolite rather, and the other is just a regular amphibolite. Hornblende, garnet, and plagioclase are the three major minerals. You can see all three of those. I'll put those next in line there. So you got those. Those are in the lower crust or the middle crust. Then you melt those, okay? And you produce continental crust. And what you produce is TTG, or a tonalite. And I've got a piece of tonalite here to look at, okay? So we'll put that next in line. And I don't have it on there, but you can melt that TTG and you can get a nice case bar rich granite, okay? Partially melt that. So that's next in line. So to get a granite like this, you've got a long ways to go from the mantle. You don't go straight from the mantle to a granite. You've got stages in there, and this is the minimum number of stages. You may have many more than that. And you can leave some restite behind in the mantle down here when you do that. And I've got a piece of restite here. This is a Hartsbergite, it's known as. It's an ultramafic rock which the garnet and the clinopyroxene have been melted out, and they've left olivine and orthopyroxene in here. You can see some orthopyroxene. This is a nodule from a kimberlite in southern New Mexico, actually. So we'll put that here. So I'm going to just move these rocks all around, and then have you guys come up later and put them in the right order and list all the minerals in them, okay? Or the major minerals.
Can we start with Barbara?
We start on this side, yeah. Okay, one thing that I've been interested in recent years is looking at the tectonic settings that are preserved in collisional origins. And we've been looking at collisional origins through time, and this is a graph that summarizes the tectonic settings from 1,000 million years ago to 2,100 million years ago, this very interesting time gap between two supercontinents. And I've divided them into three categories here: continental arcs, oceanic settings, and then the stuff that's reworked Archean. And as you can see on here, continental arcs with an average of 60% comprise most of what we see preserved in our collisional origins. Most of it.
What do you mean by continental arcs?
These are arcs that form around continental margins, like the Andes today. They're built on continental crust. Oceanic arcs would be arcs that are built out in the ocean, like the Izubanan arc system, for instance. I think Bob Stern. Is Bob here, by the way?
Next week.
Huh.
So how would you put a place like British Columbia in there?
Well,
It's sort of
it's a problem because you have terrains accreted there, you see. The data I've seen for most of the arc material in British Columbia is continental margin, but there are certainly examples of oceanic arc that have been accreted in British Columbia and Alaska. So it's a complicated area where you have terrain accretion. You can't really say that it's just this. The modern arc, by the modern arc, the last 30 million years, from the Garibaldis on up into Alaska, is certainly a continental arc. It's built on continental crust.
So if you go way back in time, how are you actually identifying whether it's a continental island, or is it by geochemistry, or is it by the geologic context?
Both. It's both. And I'm just going to talk about that in my other lecture more. But certainly that's an important question. That is a very important question, and there's a lot of uncertainty in some of these. The oceanic settings here are oceanic arcs, oceanic crust, oceanic plateau material that's left over. The reworked material is older crust. Okay. Now, if you look at the growth rate of continents, these are some curves that have been published in the literature, not all of them. Somebody else recently compiled a graph that had so many curves in here that you couldn't read the graph, so I decided just to choose a few that represent some of the extremes. What we have here is cumulative amount of continental crust with time, and this is wrong over here. This is 8/10, this is 6/10, this is 4/10, this is 2/10. So keep that in mind. If we take a look at Bill Feist's curve in 1978, this is an amazing idea at that time. Today it's not quite so amazing. A lot of people are thinking like this. The continents came out very early. He's got them coming out back here at 4.5 billion years ago. Maybe that's too early. And they grew very rapidly. And notice they go over 100%. And then from this time on, you just recycle them back into the mantle. And Dick Armstrong was one that championed this, starting him a little bit earlier, or a little bit later. Pat Hurley at MIT, on the other hand, said, no, that's not how it happens at all. Continents have grown slightly. They begin to grow a little bit, and they've grown most in the last billion years or so. We now know that the potassium, argon, and rubidium, strontium ages, which this was based on, are really recording the thermal history of the continents and the preservation of rocks in that thermal history, and not the juvenile crust. And then there have been many others in here. Here's one that Ian Campbell proposed, which is a one-step formation at about 3.5 billion years ago. And there are many, many others in here. We've proposed one which I didn't show, which is many steps. Okay. So you name it, and you can probably find somebody's curve in there for how continents have grown at time. That doesn't give the outside world much certainty that we know much about how continents grow when we have so many different models that are in there. Let me talk a little bit about lutetium hafnium. I'm not going to say a great deal about this because Rick Carlson, Rick's not here, I guess, but he told me he's going to cover the model ages and epsilon data in detail. And indeed, it would take a long time to go into this. And so I guess I would rather leave it because he's going to talk about that. But I do want to hit on a couple of things for the graphs that I'm going to show. And incidentally, the samarium 147 to neodymium 143, the same systematics apply as they do for the lutetium hafnium system. This system is very important in the zircons we've been talking about. We define a term called epsilon here, which is really a measure of the 176-177 ratio. 176 is the daughter isotope. 177 is a stable isotope we normalize to in the sample, and it's normalized in this case to average chondritic meteorites. So it's just a way of comparing that ratio to chondritic meteorites, which is something that's primitive, okay? On the graphs I'm going to show here, if epsilon hafnium is positive, this is usually taken to reflect largely juvenile crust. There's a whole spectrum between positive and negative, so it's all degrees of juvenility, if you want to think of that. If it's negative, we're talking about largely reworked crust. If we come to model ages now, if we take the radioactive decay equation and write it in terms of the lutetium hafnium system, the 176-177 ratio in the sample is equal to that ratio in the initial rock, that's what the sub I stands for, plus this term, which is what records what has decayed over the time interval t, given the decay constant lambda here, which has been measured. Now, a model age means that we assume this initial value here, okay, to calculate that t. We assume this initial value. Now, then, generally today, that's assumed to represent depleted mantle. That's mantle that we've extracted some amount of continental crust from over time. It doesn't need to be depleted mantle. It could be, say, chondritic mantle. Or it could be some specialized composition of mantle that you've created that you think the continental crust has come out of, just so you use the same material to calculate all of your mantle model ages. But model ages you've got to be very careful of. They're used indiscriminately a lot of the time in the literature today. And you have to remember that they're completely dependent upon what you assume there for that initial ratio. And so they're not like a zircon age or some of the other isotopic ages where we can identify this ratio by some other means. Here, we're making a model as to how continents have been extracted out of the mantle, and that model is what we use to calculate these model ages. I think Rick will say a lot more about how we go about this, but let me just show this simplified diagram here to show some of the complications. This is where epsilon hafnium is plotted on the vertical axis. This is positive space, this is negative space, and this is time down here. Shown on here is the uniform chondritic reservoir, because that's where we're normalizing to. It's 0, of course. And this is the growth curve of depleted mantle, okay? And this depends on the lutetium hafnium ratio that you use back here. It may be a little bit steeper in this. It may be a little shallower. It's probably curved. It's probably not a straight line because that has changed probably with time. So this is a simplified version of it here. If we take a sample that we analyze, we'll call it S down here. If we calculate a model age for that sample, let's say, started out back here at depleted mantle, and with time it has evolved along this curve with some lutetium hafnium ratio. And that can be an uncertainty too, that lutetium hafnium ratio. That's one way we could get the sample, is by having it start at point M and evolve with time down here. At this point, that rock is melted, and we form zircons in it, and we lock in that signature, which when today, if we keep on doing that, it would be way down here someplace. Sample 2, we calculate a model age for that. That's back here, isn't it? Okay. In fact, any sample on here, you can calculate a model age given a lutetium hafnium ratio, and extrapolating back to DM or back to Chur or back to some other composition. However, there's another way you can explain this, and that's by mixing. We can form juvenile material along the depleted mantle curve here, where the green dot is. We can mix that with some older material down here, older continental crust, and get point S. So it could be a mixing line, or it could be the results of growth. And there's a lot of controversy today as to which of these it may be. And in some instances, we probably have both represented on a diagram. As I'm going to show you on the next diagram, especially where we see the zircon age peaks, there's a large concentration of vertical populations of data. Those large concentrations suggest to me that much of this might be explained by mixing and not by model ages. This is a graph. I've forgotten how many data points we had on here. There's probably about 10,000 on this graph of our 40,000 when I put this together. Here's our epsilon hafnium versus age. Here's some continental growth lines for reference with that lutetium-hafnium ratio. These red dots represent the major peaks, the major zircon peaks. The black lines are, I think, 2 standard deviations of variation in those peaks. But what I want to call your attention to here is 2 things. The dense population of data in vertical arrays. That certainly, to me, suggests that mixing might be important here. Why should you get such dense population? And you even get that in areas where you don't have peaks, like in here and here. If you look at individual locations, you get vertical population. Let me just finish, and then I'll come back to questions on this. The other thing I want to point out here is these data which fall way down here are extremely negative values. How did they get there? Well, if we calculate model ages for them, as the red arrow suggests, they must have come from something very early back here. This one back around 4.2, for instance. So these data become very interesting and important because they may be our only way, using this system, of getting at where the earliest continental crust actually appeared in the picture, okay? So if we take these low values and we extrapolate them back to their model ages, suggests we had some continental crust back here. However, let me point out that continental crust is not equivalent to continents. This is a big area of discussion today, is how much continental crust do you have to get these guys down here? Do you have a continent, or do you have a granite that's exposed in, say, an oceanic arc? And that granite gave rise to some of this material down here. So it doesn't tell us the volume we have. And this is where there's been a great amount of debate. Now, I don't have on here the Jack Hill zircons. The Jack Hill zircons, many of them plot in between about 3.8 and 4. There's one of them that goes up to 4.4, but most of them are between about 3.9 and 4.2. And they would fall right in here, okay? And have been used and misused or misinterpreted, I think, to suggest that some individuals have suggested that they represent continents, that we had big continents back here. Maybe we did. And those continents all been recycled today, and all these zircons have been recycled back into the mantle, except a very few in this area. If you go to the Jack Hills area, and I've worked with some of the people there, Simon Wilde assures me that there's only one small horizon in the sedimentary rocks there, in the quartzites. It's about 1.5 feet thick. That all these hundreds of zircons that Mark Harrison has analyzed and published come from that one little thin layer. If you go out of that, you don't find any of them. And that's the reason many of the people who've worked in this area have not found the really old zircons, because you've got to know right where to go to find the old zircon layer. So, again, I'd like to emphasize, and this was the same thing that I was trying to emphasize on the peaks. The density of data on here is dependent upon where people have worked. If you go to that one little layer and you collect tons of rock out of there, incidentally, the number of old zircons in that little layer is very small. It's a few percent. Most of them are younger than that. And you process tons of rock, and you keep processing it and processing it and processing it. What are you going to do? You're going to have a whole huge population of data here from one little tiny layer, okay? Somebody had a question back here, I forget, or several questions.
First question I was going to ask you, but I think I remember the second question. So it looks like they're defined based on the mean in each of those.
I'm sorry, I can't quite hear you.
So the peaks you've chosen with your red boxes look like they're based on the means. So is the mean or the median given the discussion we just had about boxes?
We've done it both ways, and it didn't matter too much. I can't remember whether these are means or medians. I think these are actually mean values. We've done both, like I say. I could show you another graph, and there's usually not a great deal of difference between the mean and the median. So they're pretty well bell-shaped curves. In a few cases, there is over here, for instance, there'd be a difference because you've got all this spectrum down here between the mean and median.
So the sampling's hugely biased.
Why
Why would you have that?
would you have what?
So given the discussion you just had about bias and how these things are collected based on where people get I'm just wondering statistically, how do we think about where you put these red squares?
Like I say, you can put them. You can make a graph like this for either the mean or the median. And in most instances here, there's not much difference in the two.
So why have them on the plot?
I put them on there to show you where the zircon age peaks were from the previous graph. Yeah.
A little bit different question, but what you just said about something could come from a granite in an oceanic arc. At what point do you say that something is continent?
That's a good question. Is Madagascar a continent?
I mean, how do you think about that?
Yeah.
You're talking about what?
How big does it have to be? Is Greenland a continent? Is Madagascar a continent? Where does the boundary? I don't know. It depends on how you define it.
I mean, those are clearly continental crusts.
They're continental crust, yeah, right. Yeah.
So it doesn't matter whether they're a continent, in my opinion.
Yeah.
They could, someday they'll be part of a big continent, probably. They probably were part of a big continent. So, but I think what you're asking is more like, how do you know that it's continental crust as opposed to something out in the middle of the ocean basin that doesn't survive?
Or if you get enough of that granite in your oceanic arc, is it then continental? Like, what?
Well, today we know there are some granitoids that form in oceanic
How much
arcs.
do you have to differentiate something before you're willing to call it continental crust instead of something oceanic?
I can mention something about this in my other talk, but there's some really distinct geochemical differences from granitoids that form in oceanic arcs and those that form in continental margin arcs.
Okay, but like, I guess I have a more conceptual question, right? Like, is it a continent at the point at which it becomes very difficult to subduct, or is it a continent at the point at which the silicate content is, I mean, those are related, right? But like, how do you, in the end, I might not care whether it was formed in an ocean or formed in a continental arc, because now something that we call continental has a different origin, but.
Yeah, well, there are clearly different ways to define continents. There are clearly different ways to do that. And I think one of the things we have to think about is how should we define continents that's the most meaningful in terms of how we're studying them.
So what would your insight on that be? I guess
Well, what I was referring to back here is whether you're thinking of continents coming out very rapidly, like in the Bill Fife model, and suddenly you've got continents, okay, covering, a third of the Earth's surface. And then or maybe more than that in his model, and then you recycle them back into the mantle with time. As opposed to a little tiny area where you've got a granite, okay? And that could be in an oceanic plateau, it could be in an oceanic arc, it could be some tectonic setting that we don't understand. But it's a little tiny area, okay? So it's a matter of size that we're talking about. And the zircon population alone is not going to tell you that size, okay?
Well, Iceland might be a good example.
Yeah, excellent.
Is Iceland a continent or not?
Yeah, right.
Because it has granites.
Yeah. It has granite, has felsic volcanics, and
I guess it depends on what ultimately happens in Iceland.
yeah.
all right, all the pressure's on Iceland.
Excited.
Somebody back here had a.
On a related note to this point about the island versus continental arcs, somebody mentioned British Columbia earlier, and I mean, if you looked at that, a billion years from now, when it's just probably a big mess, you probably wouldn't be able to pick out continental arc granites within that belt because they were built on top of an accreted oceanic section. It would basically just look like a bunch of oceanic arc rocks.
Yeah, indeed, that could lead to complications. I can see that. The thing is, continental granitoids have distinct geochemical characteristics. A lot of people have shown that. And when you start to see continental these granitoids with this sort of geochemistry, you start thinking continent. Southern California batholith that Sin-T has worked on and others have worked on have very characteristic compositional features of continental crust.
With regards to the model ages stuff, you make a really good point about the fact that the depleted mantle itself is really sort of model dependent, and we don't know it very well. But I think probably an equally important thing with regards to using zircons is that the parent-daughter ratio, lutetium-hafnium ratio, is basically just assumed. I mean, so that those arrows that we have that project diagonally, they could have a different slope.
Yeah, that's what I meant when I said you had to be careful about lutetium-hafnium ratio, because whether you use the zircon ratio or you use the ratio of the rock it evolved in, you see, can make a difference in where your model age comes out. And indeed, and we don't know in a lot of cases. And today, very often in the literature, people will calculate a model age with each of those lutetium-hafnium ratios, so you can see the difference. Okay, I thought I'd show you a picture of an old rock. Back in the early 1990s, when Sam Bowring discovered the Acasta gneiss age, he was the first to do that, and just by chance, he happened to pick up a piece of it. A few years later, I visited him. This is one of his grad students from MIT. This is a piece of that now. This looks very much like the previous picture I showed you from Zimbabwe. This is a typical TTG, very, very complicated. Lots of different components in here, and there's been a lot of discussion. Of course, this is where our 4 billion-year-old zircon ages come from, is out of a rock like this. And he took me to the actual outcrop, which wasn't on this island, it was on another island, where he got the 4 billion-year-old age. And we discussed a lot then, and a lot more discussion has appeared in recent years when others have come into this area and analyzed zircons from it, as to whether these zircons formed in situ or whether they're later metamorphic zircons. And he assures me there are some that he found in situ, and the ones that were 4 billion years in age, there were 2 or 3 of them in that age range, he interpreted as being in situ in the rock. They formed at the same time the magma crystallized, the tonalite magma crystallized to give rise to the rock. Certainly they have overgrowths on them. And these overgrowths are younger. They're 3 point something on the overgrowths. Some of the later workers, incidentally, have not found 4 billion-year-old zircons. So we're back to a Jack Hills thing, you know. I mean, maybe there's just a little bit of a terrain someplace there in the Acasta gneiss complex that has some old ages. And if you don't happen to get into that right spot, you don't find them.
What about the depth of the crystallization of this rock?
The depth?
The depth of crystallization. When you start that?
At least then there not been any thermal barometry done, but probably mid-crustal is the mineralogy that's in this. There are some metasediments in this that have garnet and such in it that you could do some thermal barometry with, I think. But I'd say mid-crustal would be the depth. We're talking about, 10 to 15 kilometers, 20 max maybe.
It's worth pointing out that would be the depth at which these rocks were metamorphosed, but
Yes.
where the granite actually crystallized, I don't think we really
Yeah,
know.
that's right, yes. So if we look at the zircon ages, this is a plot of actually our collaborators at Macquarie University. These are detrital zircon ages showing the peaks that we've talked about. And I superimposed on here model ages, hafnium model ages. And you see they're very different from each other. Here we have the pronounced peaks. Here we don't. In fact, if these model ages are interpreted as extraction ages from the mantle, it would look like what? That most of the continental crust was extracted between about a little over 3 billion years ago and 2 billion years or so in this area here.
And there's no attempt to somehow correct for the mixing.
These are sort of these are the zircon ages, and these are the depleted mantle ages.
But you showed earlier that a depleted mantle model age may represent the time of crust extraction, or it could represent mixing.
Yeah, these assume that it's the time of crust extraction.
Right. So no attempt
Now, what I've done on this graph is I've pulled together all of our data that we have and that others have published, both in terms of hafnium and neodymium. Now, neodymium systematics are basically the same as the hafnium systematics. I should say a little bit of something about filtering with oxygen isotope data. I think Rick's going to talk about that too, so I don't want to dwell on it too long. But a lot of the zircons we know come from reworked sources. They don't come from mantle sources. And one way of picking those out has been shown to look at the oxygen isotope composition of the zircon. And the oxygen isotope window, a small window which is characteristic of the mantle, we just take the zircons in that window and anything that's higher than that, that has a higher epsilon or lower epsilon than that, we assume it comes from our crust. This database here, I've brought together all the published data that we have oxygen isotopes on the same zircons, but this represents all of the data, okay? And what we have down here is the depleted mantle age, depleted mantle hafnium age. And you'll notice that there are a couple of major peaks in here, one between 3 and 3.5, and another one between 1.5 and 2 or so over here. And if we use the entire database for hafnium, it looks very much like this.
Can I ask a question?
Sure.
You got me confused because the previous diagram you showed a curve for hafnium model ages. It looks different from this. So why is it different?
The database is different. This is the most complete, and also this is only those which oxygen isotope data are available for. The other one was everything that was available, but that was 6 years ago.
What kind of geographic areas are represented?
These are global. I've actually broken it down by geographic. Every continent, including Antarctica, is represented in there. Now, if we put our filter in there, okay, what I've done here is just taken the data out of here that pass the mantle filter, which is 4.5 to 6.5 per mil in terms of delta O18. It looks very similar, except this peak is much lower, okay, much less well developed, much more robust. But the older peak appears to be hanging in there. Here's the same sort of data for neodymium now. In fact, I just updated, you can see the date there, 6/10/13. We now have about 5,000 neodymium. Now, neodymium data differ from hafnium in as follows. Hafnium comes from zircons, okay? And in this case, detrital zircons. And neodymium comes from bedrock. So we know where it comes from. We don't have to guess where the detrital zircons come from. And it comes from granitoids and some felsic metasediments. And if you look at this, then, these are neodymium model ages. You get something that looks very similar to that, don't you? There's a younger peak that shows up here that is not in there, or it may be there. They may not just be well developed. But if we compare all of these now, and especially these two, we see a similarity in where this older peak is, here 3 to 3.5. Here it's a little younger, maybe, around 3. But interestingly enough, if those two are interpreted to be meaningful in terms of extraction age of continental crust from the mantle, it would suggest that a large amount of continental crust was extracted from the mantle between 2.5 or 3 billion years ago and 3.5 billion years ago. What these mean, it's not clear yet, because this is not sorted by oxygen. But if this is right, in the neodymium, it would mean that we also had some continental crust that formed between 2 and 2.5 billion years ago, and perhaps a little pulse here. However, this suffers from sampling bias. The neodymium data is where people have worked. And last time I updated this in the last 6 months, a lot of this data comes from China now. We have tremendous amounts of data coming from China on neodymium now. And I'm going to actually separate this diagram out into the data that comes from China and from not from China, see what it looks like. It'll be interesting. But some of these peaks, this over here comes from the Central Asian origin, a lot of these data. A lot of these data come from the Arabian-Nubian Shield. So there's certainly geographic biases built into this, sampling biases. Does somebody have a question or comment? I just wanted to show you some osmium data. Again, Rick's going to talk about this, so I'm not going to talk about it in detail. But if we have events that form continental crust, they should leave a record in the mantle. And osmium isotopes provide a method for us to look at that event or those sort of events in the mantle. Rhenium-187 decays to osmium-187. Rhenium is very incompatible in the mantle. Osmium is not. So when you melt in the mantle, you actually can lose the rhenium. In other words, you lose the parent isotope. This gives rise to what is known as a rhenium depletion age in the mantle. This is the data that Bill Griffin has recently compiled from his lab only, I think, on mantle sulfides. Okay, and if you look at this on the relative probability graph, you get a distribution here with a peak between 2.5 and 3.5 billion years ago. This would represent rhenium depletion ages, and rhenium being incompatible would go on up into the crust. So it's interesting that we get this peak in the same place, roughly, that we got the hafnium model age peak and the neodymium model age peak. I think that's important, probably. Yeah.
On the same by sampling?
No, it's not. No. Most of these data from Bill's data come from South Africa and Siberia. Okay.
Which are Archean.
Yeah. Yeah. That's right. So there could be definitely a sample. You can see some peaks coming in over here, and that may be sampling bias. Yeah.
Ken,
yeah.
I'm going to put a very strong statement out there, but it's my bias, but I want it out there. I don't hold this to be useful at all.
Okay.
And the reason is because
you need to talk with Bill about that.
And it should be at least known to a spectrum. I mean, geochemists often will disagree with one another, but I think what you've talked about in terms of hafnium model age, neodymium model age, and that kind of work is really a robust geochemical indicator. This one suffers from extreme problems, not just minor ones.
Mm-hmm.
I'd rather not go into detail.
Okay, I'd be interested.
Compromise the answers.
I'd be interested in hearing what those are eventually.
I'll just actually clarify one thing, though. It was noticed very early on, the earliest rhenium-osmium studies of mantle xenoliths, which were performed on cratonic mantle xenoliths, that the ages of the mantle xenoliths were similar to the age of the overlying crust, which is exactly what you're saying
Mm-hmm.
here, in a sense. So that's not a surprise. The problem comes when you go into areas that are not Archean in age, and you get model ages there that, you might get a Proterozoic model age, but interpreting that in terms of when that piece of mantle formed is very difficult, because today you go into the modern convecting upper mantle, abyssal peridotites, you see Proterozoic ages.
Mm-hmm.
Okay, so osmium, there's these little bits of osmium that are preserved in modern day convecting upper mantle that have old model ages. You don't get Archean, but you get right back to the Archean. So interpreting the Archean data is fairly straightforward, but once you get post-Archean, it's very difficult to interpret those model ages.
That's a good precaution. A recent paper that just came out that I thought was interesting in Nature by Pujol et al. Looked at potassium argon. Now, we almost thought this is a past system in terms of understanding continental evolution, but they looked at the argon 40-36 ratio. 40 is the radiogenic argon. It comes from potassium. 36 is a stable isotope. And they felt they found some hydrothermal quartzes in Western Australia, of which the fluid inclusions in the quartz they felt were actually trapped in there during the Archean rather than added into there by later metamorphic processes. And they got the present day ratio is 298 for this ratio in the atmosphere, and they got a ratio in these around 140 someplace here in these ratios. Maybe some of you saw this paper. And if they assign that to a 3.5 billion year old age, which is the age of the section it comes out of, this sort of gives the uncertainty of that 40-36 ratio. However, there are later metamorphic overprints and igneous events at 3 and 2.7, so they recalculated what the ratio would be at these two younger ages. and plotted this on here. Well, they have a model that you can go from this to crustal extraction of continental crust, putting the potassium up in the continental crust. It's a fairly complex model, but you can have a look at it in this 6 June 2013 issue of Nature if you're interested in that. Anyway, here's their graph down here in the percent of continental crust. These are for different degassing rates of continental crust. And here's the initial ratio, 140 or so, and the two recalculated ratios over here. It's interesting that they have rapid growth of continental crust. Their time scale, incidentally, they've got Geiger years here rather than GA, so this is 0, and this is, if this was 4.5 billion years ago, this would be 3.5 billion years ago, this would be 2.5 billion years ago. So interestingly enough, their model predicts growth rate of continental crust at the same time the hafnium and the neodymium predict rapid growth rate of continental crust. I'm not going to defend their model. If you're interested in that, you can go to that issue of Nature and see it. So if we go back to our cumulative preservation curve, and I think that's what these are, cumulative preservation curves, I've added our data from our 2010 paper in here, which would suggest rapid growth of continental crust between from the model ages with bumps from then on. The bumps, there'd be 2 or 3 more bumps here, they don't show up. Now, I just wanted to say something about underplating. I guess I'm just about out of time here, and I'm about maybe 2/3 of the way through this, but we'll see. One of the ways of getting at underplating is to look at neodymium in terms of mafic dike systems and mafic intrusions in the crust. And over here I have an epsilon neodymium graph, one for mafic igneous rocks. These are largely intrusives or their metamorphic equivalents. And then over here I have it for felsic igneous rocks and metasediments. This is like the one we just looked at for hafnium, except this is neodymium. And I've got a running average on here where the density of the data are. I've forgotten how many data points. It looks like when I compile this, there's 5,900 data points on the neodymium graph. And you'll notice that most of these hang in there about the same, close to the chondritic curve, until you get to rocks that are younger than 1,000 million years. And then we get a substantial reworked signature coming in here, which is interesting. It appears to occur after 1,000 million years. If we look at the mafic igneous rocks, and we see that these guys are dominantly up in the juvenile field, with one exception here, and that comes from one geographic location. I don't recall where that's at. I think it was in China. They're dominantly in the juvenile field. That's important if this turns out to be robust, because if these dikes and sills are indicative of what's going on deeper in the crust, in other words, underplating of mafic material in the crust, they would suggest that younger underplates could be important in crustal growth. You can see most of them are up here very close to the depleted mantle curve. And this is something I think we need to give some careful thought to in the future. So, based on hafnium neodymium model ages, greater than 70% of the continental crust appears to have been produced between 3.5 and 2.5 million years ago. And then I'm going to ask this question. What happened after 2.5 million years ago? Did the production rate decline, or did mantle recycling exceed production, or both? And this is something I think we need to focus on. I just wanted to say something about recycling here. If I could go on for a little longer, or what do you think? What's that? Another 5 minutes and jam 20 minutes worth of talking. Anyway, we now know that continental crust is recycled in the mantle. Just a little bit of background on that. Dave Scholl with the USGS has been working around the Pacific for many years, and I have some slides a little bit further to show some of his work, but I guess I'm not going to have time to show them now, but we can see them later. But his studies have suggested that we're recycling continental crust in the past 200 million years back into the mantle at about the same rate we're forming new continental crust around the Pacific. Clearly something had to be different in the past if his results are correct, or we wouldn't have any continents. Sometime the production rates had to be greater than the recycling rates. So if we look at the mass balance equation here, the net continental growth rate, which is really the net preservation rate, let's suppose that that's equivalent to the zircon peaks that we see, is equal to the juvenile crust extraction rate, E, which will be some curve like this. It may not be this one, maybe one of those others, or some other curve, which gives us the rate of juvenile crust extraction from the mantle, minus the rate that continental crust is recycled back into the mantle, which I've broken up into three categories here: sediment subduction, subduction erosion, and lithosphere delamination. Okay? So if we can start to estimate these three guys here, even if we just have these two, and there have been a couple of papers recently that have taken these two curves and subtracted and solved this equation for R back here, see what it looks like, how much has been recycled back into the mantle. That just shows subduction, erosion, and sediment subduction. And this shows mafic material produced at ocean ridges when you split a supercontinent up, and how much material, mafic material, you might get underneath that supercontinent, which is not accounted for in our growth models. And this is one of Bob Stern and Dave Scholl's papers where they look at the mass balance here, and I won't go through all of this other than to say their additions over here and their subtractions down here are roughly the same. Looks like we're losing material about the same way we're gaining it. His work in South America here suggests that the edge of the Peru-Chile Trench was out here some 250 million years ago, and by subduction, erosion, and probably delamination, 600 kilometers has disappeared in the last 250 million years, most of it in the last 100 million years as the South Atlantic has been opening. This is a graph showing the zircon ages for Laurentia. There's always been a minimum here at 1500 to 1600. The question is what that minima represents. If we look at the neodymium ages for that, we see neodymium model ages, there is no minimum. This suggests that maybe there really was crust produced at that time, but it didn't survive for some reason. Maybe it was recycled into the mantle. This is one of Dave Evans' reconstructions of Rodinia here. Here's Hudson Bay for reference. And you can see the ages of the various origins on here, what we call the Great Proterozoic accretionary origin. Here's the orange, which is 1.6 to 1.5. We don't find any evidence of it along most of the origin here. There's a couple of small spots, one in Quebec and one in Labrador. And the question is, could those be what's left over after most of this was recycled back into the mantle? And one possible way of thinking about this on a broader scale is that these peaks represent preservation peaks in collisional origins where we preserve continental crust. And the minima here represent recycling. When you split a supercontinent apart, for instance, and you don't get that represented in the zircon record virtually at all, could these represent times when we're recycling continental crust back into the record? So these would be preservation peaks and recycling peaks. And just to summarize a few things that we've gone over here. Number one, zircon, uranium, lead ages, both igneous and detrital, have widespread distributions with major peaks at those 5 times. These 5 ages correlate with supercontinent formation, and with the exception of the 2700, probably represent increased preservation of supercontinents rather than spikes in continental growth. 2700 would probably be both. Juvenile continental crust forms chiefly at retreating origins, and recycling occurs in advancing. I didn't get a chance to talk about that. We can look at that if anybody's interested. Today, continental crust is being recycled into mantle as fast as it's extracted. Based on hafnium isotopes, about 70% of the continental crust, between 3.5 and 2.5. minima between zircon age peaks may reflect recycling of continental crust into the mantle during supercontinent breakup. And then I've got a few questions here to think about, okay? How can we determine the abundance of stagnant lid continental crust that may have given rise to these early zircons? If, in fact, the early zircons represent continental crust, did it come in a plate tectonic regime, or did it not come in a plate tectonic regime? If plate tectonics didn't start till around 3 billion years ago, I'm going to talk about that in my other lecture, these may have actually formed in a stagnant lid regime. And is there some way we can tell them apart? How can we estimate the importance of underplating of continental crust to the growth of continents? I've emphasized this several times here, and I think this is an area that a lot more effort needs to go into. And it may be that here a combination of seismology and geochemistry might be the way to approach this, actually. How do we distinguish mixing from isotopic growth on the Hafnium and Indianium curves? And are the model ages really ages of separation of continental crust from the mantle? This is going to be a more difficult one to handle. But I think it's a question we always have to ask. Why does the supercontinent cycle speed up? I haven't had a chance to talk about this, but it appears to speed up after 600 million years ago. I guess I'll stop there. I've got a lot more slides, but what do we want to do now? Go into a open discussion mode, or what?
Well, we got.